Okay, so this alkyne, in this lecture we'll talk about alkynes. So alkynes means carbon triple bond. Okay, so the carbons are here sp hybridized, and their structure are linear. Okay, so suppose if you have carbon here, all these four carbon atoms are in one line. Okay, so this is the alkyne. So alkynes are considered at the parent bonds of alkane. Okay, so here A of alkane is removed and Y is added. Okay, so here it will be al, so this A is replaced by Y, so it's alkyne. So suppose if you have, at least you need two carbons to be one alkyne, because we need a carbon-carbon triple bond. So like this is ethane. Okay, if we have this one, then this A you just remove by Y, so this will be called ethyne. Okay, so for this simple alkane, so this is the nomenclature. So similarly, propane, propyne, butane, butane, pentane, pentyne, hexane, hexyne, and so on. So, so all those nomenclatures of alkane rules, those are followed, and just except you need to keep put yine. Okay. And numbering will start to the carbon that can give the least possible number to um, the alkane, functional group. So let's say, so here like this molecule 1, 2, 3, 4, 5, 6. So I'm not showing all the hydrogens. So this will be called hex 2-ine. Okay, and so on. So when you have a carbon, if two double bonds are two triple bonds are there, then that will be called diene. Okay, let's say this one here. Now you have CH3 here, and suppose hydrogen here. So numbering will start from this. So you can give the least possible number to both the triple bond. So this is also hex, so diene. So this molecule will be called hex 1,4 diene. Okay, and if there is a double bond in this, okay, and let's say like this double bond, here you have two double bonds, so this molecule will be called, say, double bond in alkene en, and this is ine, so this will be called enine. Okay, enine. So exact, so this ine will come later, and before that it will come in. But numbering will start from the double bond side. So like this 1, 2, 3, 4, 5. Okay. Numbering will start from the alkene side, but it will end with the ine. So this molecule called pent 1N and 4-ine. Okay, so this is the simple nomenclature will be followed. So if the molecules, if it is cyclic, let's say if you have like this triple bond is there, okay, then you need to just put the cyclo, okay, letter cyclo. Let's say here this is CH3 is present here. So what will you so numbering will start here from here, so that the substituent also get least possible number, same as alkene. So it will be 1 2 3 4 5 6 7 8 9 10. Okay, so what it will this will be called cyclo 3 methyl. So substituent will come at the very first, 3 methyl cyclo de dec dec 1 I. Okay, so this is the nomenclature of alkenes. Now let's talk about the synthesis of alkene. How do we make alkenes? Sorry, alkynes. So alkynes are, this is a trivial synthesis. There are several other methods, but we'll talk just only one. Suppose if you have a carbon-carbon double bond like this molecule, and you have hydrogen. So from alkene to alkyne. So first you need to add bromine. You know that bromine will be added. So bromine will be added in a trans fashion like this. Okay. Then if you take a strong base like KOH, okay, so what will happen? This will undergo E2 elimination. Okay, E2 elimination. Remember, in the next chapter it will come. E2 elimination. So this O minus will take this proton. This will come here. This will leave. So again, it will form an alkene, but the only difference will be that it will have one bromine. See this from previous alkene. Then you take another base, a stronger base, or sometimes the same base can be used, the KOH, but we need a strong heating condition. So sodium amide can take this proton and this will leave. So this will form a triple bond. Okay, so alkene, so it's a dibromoalkane, and then again alkene but bromo, vinyl bromoalkene derivative, which it will give alkyne. So this is a two-step synthesis for this. Now come to the reactions. See, before talking about the reactions of alkyne, you should recall the reactions of alkene. So many reactions, they are very close, very similar. First, we'll talk about the addition reactions. Okay, so because that alkynes have the pi bond, so they can go easy 2 pi bonds, pi bond, pi bond. They can go easy addition reaction. Let's say first is addition of an acid. Okay, so this is a symmetrical alkene. So let's take, suppose this one here, you have hydrogen. So addition will take place according to same as Markovnikov's rules. The first pi bond will add and it will get the positive charge, and this will make a vinyl carbocation that is very, very unstable. Okay, so it's minus, this will be added and Br will form, and then you have a double bond. So now it's an alkene. Again, second molecule of HBr will be added. And again, this addition and carbocation formation take, will take place according to Markovnikov's rule. So this carbocation will form. Okay, this carbocation is very stable. In addition to hyperconjugation, okay, this carbocation is stable by resonance with the halogen. Okay, this is resonance, and okay, and you have here there's a Br minus. So Br minus will add in the second step, and the product will be BrBrCH3. So this is called geminal dibromide. So two bromos are present on the same carbon. Okay, geminal dibromide, the product. Okay, HBr. Similarly, if you will add HCl, so two molecules of HCl will be added, and you'll get the same product. Two, so it will be 2,2-dichlorobutane. Okay, so this is addition. Next, addition of water. So addition of water to a double bond takes place, a triple bond takes place. So here, suppose if you have this triple bond and you have to add water, okay. This one takes place in the presence of mercuric sulfate, okay, and sulfuric acid. Okay. This reaction here, mercuric sulfate is a catalyst, remember. Uh, I will just write here, just as a note, that addition of a double bond in the presence of mercury happens what mercuric acetate. You guys remember the last lecture, mercuric acetate, first step, and water. Second step will be the reduction, sodium borohydride reduction. Okay? Then water will be added. But here, in case of alkynes, that alkynes are more reactive than alkenes. So here the addition will be according to Markovnikov's rule, and you don't need this 1-to-1 ratio here. Just here catalytic amount is enough. Okay, and the product will be same addition of water to the double bond. Okay, and then further it will change into ketoenol tautomerism. Okay, so let's see first the mechanism here. So here you see mercury has two oxidation state. It's called mercuric sulfate. uh, 2. So what happens? This it behaves as a Lewis acid. So the triple bond is added to mercury. Okay. So what will happen? The more substituted carbocation will form. It has mercury Hg plus. Okay. And here sulfate as will be an counterion, and here you will have the positive charge. In this positive charge, water is added. Okay. So what will happen? So this will be OH2, OH, OH. So water will be added and have a double bond. Oxygen has a positive charge, and here you have Hg plus. Okay. Then another water molecule or conjugate base take this proton, it will convert to an OH. And here this bond is also broken easily with the present because it has sulfuric acid, so it's strong acidic condition, so it has H plus. This bond will take H plus. So what will be the product? So this will be the product. Okay, and here Hg plus plus is regenerated. So that's why it's a catalyst. Okay, it can do the reaction again. Now here, what is this molecule? Remember, here you have a double bond and you have OH. Okay, such type of compounds called enol, ene, the alkene, and all alcohol, enols. Okay, and this it doesn't stay here. It rearranges to another molecule. So what to will rearrange? It will rearrange to a ketone. Okay, so we'll see this mechanism. How does it happen? So see this, you can write resonance here. This enol, I can write a resonating structure. So this will be double bond OH positive charge here, and then it will be CH2 negative charge. Okay, because here the condition is acidic. Okay, so this will take a proton from the acid, and this proton will be taken by water because it has water as well, or the conjugate base here, and then it will make this product. Okay, so here this one is a ketone. Okay, just to make clear, here you'll have this one. This bond breaks and goes the lone pair on oxygen. Okay, so this is a ketone here, and it is a enol. So enol automatically changes to ketone, and this is called keto-enol tautomerism. Tautomerism. And this tautomerism, it's a reversible reaction, but mostly in most of the cases it exists as a ketone form, little bit in enol form. Okay, so this is the addition of water and keto-enol tautomerism. So we talked about these all the addition reactions, and then let's talk about another similar reaction, another addition reaction in the presence with borate. Okay, so if you again, I will give you guys example from alkene. If you guys recall that if you have an alkene and you do hydroboration BH3 followed by oxidation H2O2 and sodium hydroxide. So what happens? Water is added as a syn addition, okay, from the same phase, both water and H and OH. Okay, so remember here both OH and H will be added from the same phase, either up or below. In this case it will be 50-50% as a racemic mixture. Okay, so here this racemic mixture here, because it reacts with a pi bond, So alkenes, similarly, alkenes have the two pi bonds. So two molecules of borane can be added. Okay. So first, you see if you have this BH3, okay, and it will be same as added that the less substituted carbon will get the small atom H, and more substituted carbon will get the big atom. Okay, so it is a hydroboration and oxidation. Hydroboration, boron and hydrogen added. So you have one more pi bond here, so one more will be added. And this will be the same way that you'll have BH2, BH2, and you have hydrogen. Okay, so then it will be oxidation with hydrogen peroxide and sodium hydroxide. So both the borons will be converted into OH. So you have now two OHs, okay, on the same carbon. Okay, this is called geminal diol. A geminal diol on the same carbon. This again, it decomposes to an aldehyde in this case. Okay, so here it will be an aldehyde. Okay, so I will write this mechanism, how this converts into an aldehyde. So see this geminal diol. See here the lone pair, one lone pair, it comes here, this OH will leave. Okay, it will be OH minus. So here it will be OH minus. Then this OH minus takes the proton and it will make this after removing one molecule of water. Okay, so this is the reaction. This is the addition of water molecule. Okay, and then here addition of addition of halogens. So one more we'll talk about. So if you have an alkyne like this, okay, and you treat it with bromine, so two same like alkene reaction, bromine will be added. Okay, and the bromine will go to less substituted carbon and you'll have a carbocation. Then this Br minus will react and you'll have BH, Br and Br. So trans bromo product will form. Both the bromines are in opposite direction. Okay, And then again, you have one more pi bond. This will react with another bromine. And again, the more substituted carbocation will form Br, H, Br, and here you have Br positive charge. Okay, and this in step again, bromine will be added, and the product will be Br, Br, and Br. Okay, tetrabromo alkane product. Okay. Similarly, if you react with chlorine, so chlorine 4 chlorine will be added across the two carbons to, sorry, it's chlorine, and then ClCl, okay, tetrachloro pentane. This will be 1, 1, 2, 2 tetrachloropentane. So this is another example of addition reactions. Okay. Again, next, the oxidation reactions. If you have a, let's say, like this molecule, here if you have ethyl, whether you take KMnO4, KMnO4 or ozone, potassium permanganate, or ozone, any one of this, or ozone, okay? This bond will be cleaved, all three bonds will be cleaved, and you'll get the acid product. Say this reaction is close to similar to alkene reaction. So you'll have acid, this product will form. So this is the example of oxidation reaction. Similarly, if you let's say just take this one, and you take any of these reagents, so what will happen? Two molecules of benzoic acid will form because they are similar. So don't worry about the mechanism. So just for this, the reagent and product, you remember. Okay. So this another important is the acidity of alkynes. Okay. See this, if you have, let's say this one here, I'll take just one. Here I'll write R, then you have an alkyne, okay? And then if you have, let's say, an alkane, so alkyne, alkene, alkane. So this carbon on concentrate on the first carbon, so it has sp hybridization. Here you have sp2 hybridization, and then this one has sp3 hybridization. So here you see one s, one p orbital. Okay, so here percent s character 50 because 1:1. Here you have 1s, 2p. So percent s character is 33.33. Okay. Here you have 1s, 3p. So percent s character is 25%. So what you are seeing, that the s character of these bonds are decreasing. Okay. Now what does it mean? See, just a very rough idea. When there is, suppose this carbon atom, it has electrons, okay, and these orbitals, and s orbital will come, then you will have p orbitals, then another s orbital, and so on. So s orbital is closer to the nucleus compared to p orbital. Okay. So here, what does it mean? Means s electrons are strong, will have more attraction with the nucleus because it's closer, and nucleus has opposite charge. So means more s character, more strong bond with the nucleus. Okay, more this, so this carbon will make a strong bond with the these electrons will make a strong bond with this carbon because it has 50% character, it is closer to the nucleus. So it means more electron density will be towards this carbon. So more electron density towards this carbon means this will have less electron density. Less electron density means polarized, so you'll have delta negative, you'll have delta positive. So here the percentage has decreased, so it means they are a little bit farther from the nucleus, so less attraction. Here this is even farthest, even least attraction. Okay, so more s character is stronger the bond, more and more polarized because of the stronger attraction of this. So when it will be polarized, so what can happen when it is polarized? If you have delta positive and delta negative charge, it means this can react with a base. So if you take a strong base, it's a sodium amide, strong base, this can take this proton, okay? And this bond can go here. The same reaction with this sodium amide with an alkene cannot happen. With this cannot happen. Okay, because those bonds are not significantly polarized. So what will happen? It will make R, carbon-carbon triple bond, negative charge, sodium will be a counterion, and then ammonia, NH3 will be the byproduct. So here you see this is the negative charge carbon, and it's a good nucleophile. It's a nucleophile. Okay, so this nucleophile can react with electrophiles. So if you have RCOO, so it's a good, but it's not very strong nucleophile. So it can react. Now if you have carbon, let's say this one here, okay, chloromethane or iodomethane or bromomethane, it can go this chlorine will leave. So alkyl methyl chloride. So what will be the product? So this COCH3 plus NaCl. So what did you see? So this we can add the methyl group. Similarly, if you react this one with benzyl chloride here, okay, so this can react, this will go, you can get this product. Okay, so this is very, very important. Okay, so it means if you have an alkene, so alkyne, if you have an alkyne like this, so first you can react this one with a strong base, sodium amide, okay, and then if you take an electrophile, let's say here ethyl bromide or ethyl chloride, ethyl iodide, anything. So this, after the formation, you can get this product. Okay. So this reaction, remember. One more thing you should keep in mind, that to react this one with the nucleus, this carbon should be primary carbon, okay? Primary alkyl halide or methyl alkyl halides are best. Methyl or primary, okay? This is here also primary. Okay? But if you take secondary like this, then here bromide, because it has two carbons attached, okay, with this, so this is more sterically hindered, and this anion cannot reach that one, okay? It cannot reach this one because it's a secondary, because of steric hindrance. Instead, what it will do, it will act as a base and will take this proton, because this is not sterically hindered, and you will get one eliminated product like E2 elimination, and then CO, and this bromine will leave, and CH. Okay, so remember this limitation, that this carbon, okay, should be primary or methyl. See, this is primary and primary or methyl here, and secondary, this will not work. Okay. Okay. Then the last part of this reduction is last part of this is the reduction reactions. So reduction reaction of triple bond is that if you take palladium 2 pi, if you take hydrogen in the presence of palladium charcoal, because it has 2 pi bonds, so two pairs of hydrogen will be added and alkane will be the product. So this is because this is, and you cannot, it happens in a stepwise process. But if we take one is called Lindlar's catalyst. Lindlar catalyst has also, it will have hydrogen as well as palladium, but this palladium is less reactive because of it is on barium sulfate, not on charcoal, barium sulfate, and it is poison with sulfur. So just remember, this catalyst is also palladium, but this is less reactive. So just hydrogen, one pair of hydrogen will be added. Okay, one pair, and the reaction will stop here. Okay, this again, if you take palladium hydrogen and regular palladium charcoal, it will make an alkyne. Okay, so now if you have, let's say this triple bond, phenyl phenyl, and you add hydrogen in the presence of Lindlar's catalyst, this only one will be added, and it will be added in a cis fashion, that both the hydrogen will be on the same side. Okay, so this reaction, but another complementary method is there, that if you use this reagent, then lithium ammonia, okay, if you have pH, phenyl means as a kind of benzene ring attached, okay. If you use lithium metal and ammonia, then hydrogens will be added in a trans fashion. Okay. So see, lithium has one electron. So what happens first? This one electron is added on one carbon. So I'm writing the mechanism. So you have this carbon. So to will break homolytically. So this carbon will get free radical, and this will have two anion pH. Okay, at initial stage, this anion is a very strong base, so it will take a proton from the solvent ammonia. Okay, so what will happen now? You will get pH, C, here free radical, hydrogen attached, and pH. Okay, in the second step, another lithium will donate one electron, so another carbon will be that anion. So now this anion will be in opposite, can write like this, pH, here you have pH. This will take a again same, it's a repetition of the previous step. It will take this proton, and this proton will come from the opposite side of this hydrogen. Okay? Why? Because in that case, these two phenyl benzene rings, they will be in opposite direction, so they will maintain their maximum distance to minimize the steric hindrance. Okay, so this will be the product. So here what you see, trans. So remember, lithium ammonia will give trans product, and in the previous slide, Lindlar's catalyst will give you the cis product. Okay, so these are the reactions of alkenes.